Well, hello and welcome again to our journey into number theory, and we've been looking at the Riemann zeta function, and we saw before that the Riemann zeta function in the complex plane has no zeros to the left of the imaginary axis and no zeros to the right of the line real part of S is 1. There are no zeros along here. We'll show soon that there are no zeros along this line either. And there are, however, zeros inside of this critical strip. The strip continues on forever. And of course the Riemann hypothesis is that the zeros, in fact, the non-trivial zeros, there are zeros here at the negative even integers, the trivial zeros, but the hypothesis claims that the only non-trivial zeros lie on this line, real part of S is a half. And just to, before we start looking at the number of zeros in the critical strip, just to come back and have a look at a little picture here. This is, I took the real and imaginary parts of zeta of a half plus it, so that is the value of zeta on the line S is a half plus it. I've got the real and imaginary parts, x is the real part, y is the imaginary part, and plotted them. And here I just let t go from 0 to 30. And we can see in this, you can see this winding around, and we can see it goes through the origin once and twice and then 3 times, and then I think that's yes, it goes through the origin 3 times there. That's between t is 0 to 30. So these points are going to represent points where the zeta function is 0 on the line S is a half plus it. Little bit slightly more dramatic picture. I did it again for t goes from 0 to 50, and once again you can see as t varies up that line, the zeta function, the values of the zeta function spin around, and we're getting lots and lots of zeros between 0 and 50. On the other hand, just for comparison, I took the line z is S is equal to a third plus it, so I move off the line a half plus it a little bit, and we look at the line S is a third plus it, and look again at the real and imaginary parts, and we'll see, you can see again here that this is winding around, but it's not going near the origin. Now of course these are not proofs, it's just a demonstration of what's happening to this Riemann zeta function along this line, at least for some small values of t, and that was again from t0 to 30, and again to be slightly more dramatic, I did it from t to be 0 to 50, and again you can see it's whizzing around the origin, but it's not going through the origin. Now again, this is not a proof, of course, it's just a demonstration of what we're talking about when we claim that the zeta function has its zeros in the critical strip along this line a half plus it, but this is a very, very difficult and deep result, and we don't even know it's true or not at the moment. It may be that if you go far enough up that line, S is a half plus it, for extremely large t, there may be zeros hiding there. The answer is we just don't know at the moment. We hope not, because as we'll see a bit later, the Riemann hypothesis has lots of important implications for the distribution of prime numbers. Okay, so I'm going to come back now to our question of the number of zeros in the critical strip. Number of zeros in the critical strip. And remember what we did was we constructed this following Riemann, we constructed this new function called psi, and psi, I'll write down the formula for it again in a moment, but this psi function is real on the line S is a half plus it, and the zeros of the zeta function are the same as the zeros of the psi function. And so because this is real, we proved that in the last section, we can use the intermediate value theorem to locate some zeros. For example, if I take psi of a half plus 14i, you can run that through a computer, you get 2 times 10 to the minus 4. And if you do a half plus 15i, then you get negative 7 times 10 to the minus 4. And that tells me there is a 0 in this interval by the intermediate value theorem, because this function psi is continuous. So in fact the first, well, inverted commas, the first 0, remember they're symmetrically placed about the real axis, but the first 0 in inverted commas is a half plus I times some number, 14.134725 and so on. And the next one is somewhere between a half plus 21i and a half plus 22i. So what we're going to look at, we're going to look at the number of zeros of this psi of s rather than zeta of s, because the zeros of each are the same. And I'm going to let n of s, this is going to be our important function here, n of s is going to denote the number of zeros of psi of s in the upper half plane, that is, we're just going to look in the upper half plane, intersected with this a region R, where R denotes a rectangle with vertices 2 plus or minus it minus 1 plus or minus it. That is, we're going to move slightly outside the critical strip. We're going to go from 2, real part 2, to real part minus 1. And we're looking outside the critical strip just for technical reasons. We know that there are no zeros, apart from the trivial ones, outside of the strip, but it's easier to look at this particular rectangle. So here's a picture of what we're doing then. Here's a little picture of what we're doing. There is our rectangle. So we're going from to rectangle with vertices minus 1 minus it up to minus 1 plus it, and then across to 2 plus it and down to 2 minus it. And we're going to let n of s be the number of zeros inside the intersection of this rectangle with the upper half plane. That is, we're going to be looking essentially at the number of zeros in the top bit here. And we're going to also define this little contour here. We're going to take this line V up here and H across to here, and we're going to call that one V union H. So that's going to be the region we're looking at. Now here is our psi function. Here is our psi of s, and psi of s is 1/2. We saw ss minus 1 times this expression, this product times the zeta function. Remember, these terms here simply made sure that this was analytic. This got rid of the poles at 1 for zeta and at 0 for gamma. We know from complex analysis, now again I'm going to call in some results from complex analysis here, that you can count the number of zeros of a complex function f, which is analytic in and on a closed contour gamma, is given by this formula. It's 1 on 2 pi I. This is the logarithmic integral of f, so it's the integral of f dashed on f. And you will know from complex analysis that this integral counts the number of zeros for you as inside this closed contour gamma. And also from complex analysis you can write this in various different ways. You can show that this is equal to 1 over 2 pi. Now this square brackets little gamma notation means the change in argument of f of z, the change in the argument of f of z as z moves around the contour gamma. This is also equal to 1 over 2 pi time of the imaginary part of the log of f of z. It's easy to show these are equal, again, as you move around the contour gamma. Okay, so that's just a result from complex analysis. If you've not seen that before, you can look that up in most books on complex analysis. So this notation denotes the change in the argument of f as z moves around the contour gamma. So if we let L be this contour that I mentioned before, this is V union H. This is essentially, if you will, it's a quarter of the contour. So it's part of the, you've got 4 of these making up the full rectangle here, and this is just going to be 1/4 of that. So that's our notation at the moment, and so L is going to be that contour. It's not a closed contour, it's just as you move up along V and then across H. Now I need some technical results, which I'm going to save time. I'm going to state without proof. The proofs of these just take a fair bit of time and they're fairly technical. The first one is this statement here, which is really just obtained from a generalization of Stirling's formula. Now you may recall Stirling's formula relates n factorial, gives an asymptotic form for n factorial. Well, gamma of x plus 1, if x is an integer, is just x factorial. So this is a kind of interpolation, if you will, of Stirling, or generalization of Stirling's formula, which you may recognize from advanced calculus courses. And if you take you replace the 1 with an alpha here, and you take the log of this and fiddle around with it, then you end up with this expression up here. So the log of gamma of z plus alpha is z plus alpha minus a half times log z minus z. This is all coming from taking logs of this. You can almost see it here. The minus z is coming from the exponential term here, and plus a half log 2 pi, well, that's coming from here, and then you get a term which is big O 1 on mod z. And that's for the argument of z between minus pi plus delta to minus 2 pi minus delta, for any bounded alpha up here, and for any delta, thinking of delta being positive here. The second result we need is what the order of this is. So this is the change of argument in zeta as you move around L, that is, that going up that quarter part of the rectangle. And that change in argument turns out to be its big O log t. Again, this is time consuming to prove, but it's in most books on complex analysis that deal in analytic number theory that deal with this particular question of the number of zeros. Now here's our big result, and it's a fascinating result, and it's very important. It says if t is bigger than 2, t, remember, was the how far up the line 2 plus it, or minus 1 plus it, you went in that rectangle. So t not equal to any of the zeros of psi. Well, there aren't any anyway in the bits that we're looking at. So we have, here's our formula for n of t. So n of t then is, this is the number of zeros inside the rectangle. It's t on 2 pi log t on 2 pi minus t on 2 pi plus, well, big O log t. Now this tells us a number of interesting things. Firstly, we notice that if t goes to infinity, this term will dominate, and so this goes to infinity as well. And that tells me immediately there are infinitely many zeros in the critical strip. Well, at least in the rectangle. Above, and we've seen before that outside of there, apart from the trivial zeros, there aren't any, so this is essentially telling us the number of zeros in the critical strip, and there are infinitely many of them. Just to give you an idea how accurate this is, I put t between 2 and 100 and got the computer to find that there are 29 such zeros inside the rectangle between t going from 2 to 100. And if you use this formula, then ignoring the remainder term here, then the error term, then n of 100 turns out to be about 28.13 using this formula. And that ain't bad. You've got 29 and 28.13, the formula says. So even though it's big O log t, it's not a bad approximation to the number of zeros. So that's what we're going to have a go at proving now. And again, the proof's slightly technical, but it's got a couple of nice ideas in it, so it's worth including here. So here is the proof. So we're going to use what we had above here, and so from the above comments we have now twice n of t, and that's because we're looking at the intersection of this big rectangle with the upper half plane. So by symmetry, once you've got a 0 in the top half of the plane, you get 1 in the bottom half. So twice n of t is going to be equal to the change in argument of psi, 1 on 2 pi times the change of argument on psi as I move through R being this rectangle. So I simply replace psi then. There's our formula for psi that we had. That's how we defined our psi of S. And I'm going to now split this using properties of argument. The argument of the product is the sum of the arguments. So this is the argument of a half SS minus 1. I'll split that up firstly, and then I've got what's left here. Now it's easy to calculate this one because you see if you go around the rectangle, once, then the change in argument is 2 pi if it was just S. You've got S squared, and that means the argument's moving at twice the speed. So as you go around the rectangle once, you're going around in a sort of circle twice, and so you're going to get 4 pi there. Now, since this one takes equal values at S and 1 minus S, and conjugate values at S plus or minus IT, we can say that the change of argument of this, as you go around the whole rectangle, is just going to be 4 times what happens, the change of argument as you go around L. This is this quarter of the rectangle. So that's why we're going to work with this L. So far, plugging everything back in, we've seen that this term here, this is 4 pi, so this gives you 2, and I'm dividing by 2 from the 2nt here. So that's going to get me back to a 1, and then just dividing, I get 1 on pi, and I'm going to split up the 3 terms in here. So back up here, I split the 3 terms into 3 bits using the argument of the product is the sum of the arguments, and so I get this expression here. So now I'm going to look at each of these in turn. Now firstly, this one here, well, this is not hard to work out because I can use that alternate form of the change of argument in L is the same as the change of argument, the imaginary part of the log of this as I move along the contour L. And I can calculate that easily. It's just minus t on 2 log pi from 0 to t, and putting in the endpoints and subtract gives me this minus a half log pi. Now for the second term, we've got the argument of gamma s, the change in argument of gamma of s on 2 around L, and again I can get the argument of this is just, oh sorry, this is also equal to the imaginary part of the log of gamma s on 2, where s goes from 2 up to a half plus it, and this is just going to be, that should in fact be, oh yeah, that's correct, that's right, so a half plus it, and that's going to be just then the imaginary part of gamma. You put in the 2 endpoints and subtract, we get this expression here, and we've got a formula for log that log of gamma that was our in our lemma that we assumed that I could replace this with this. That was from that first part of the lemma part A, and this is 0 here. And I get, of course, plus 1 on t. So here I've just used the lemma part A. I put z as it on 2 and alpha was a quarter, and this pops out. And I can simplify this expression, and this turns out to just be 1/2. We want the imaginary part of this. This is just a half t log t on 2 minus t on 2 minus pi on 8 plus big O 1 on t. Plugging all that together, then, at the moment we now have n of t is this expression minus this plus this. We've still got this term on the end to work out. But again, in the lemma, we had part B. This was the big O log t. And I can get rid of the 7/8 in that, so I can replace this expression here, all of this plus this one. I can replace all of this with big O log t, and I'm left with the desired result. So this shows that there are infinitely many zeros in the critical strip. Moreover, Selberg was able to show there is a constant c, such that for all sufficiently large t, the number of zeros on the line real part of s is a half, from t going from 0 to capital T, is at least this constant times t on 2 pi log 2 pi, log t on 2 pi, and that means that a positive proportion of zeros are on the critical line. Also, all the known zeros, the ones that have been calculated, these are all simple zeros. And that again is an unsolved problem. Are all the zeros, whether they're on the line or not, are they simple zeros? In 1970 it was shown by Montgomery that if the Riemann hypothesis is true, that is, if they all lie on the critical line, then the proportion of simple zeros on the critical line is at least 2/3. It may well be that all the zeros are simple, but again, unsolved problem, quite deep result. I'll just mention here Merton's conjecture. We'll come back and have a look at this function in a later chapter, in fact, but we're going to look at, we have mentioned this one before, this capital M of x, which is the partial sums of mu of n less or equal to x, where mu is the Möbius function. Now, we've seen before the modulus of mu of, or absolute value of mu of n is less or equal to 1. So that tells me that this capital X then, capital M of x is big O of x. Back in 1897, Mertens conjectured that the size of this was less or equal to root x. It was an obviously interesting question to look at the partial sums of this, and he claimed it was less or equal to root x. But unfortunately, nearly 100 years later, it was shown to be false, 1985, by Odzlisko and Tirielli. A weaker conjecture is that for all epsilon bigger than 0 and x bigger than 0, capital M of x is little o of x a half plus epsilon. In the sense that when I divide these two, it goes to 0 as x goes to infinity. Now it turns out that this is in fact equivalent to the Riemann hypothesis. This is equivalent to the Riemann hypothesis. It's probably false that it is big O root x. Stilches claimed this again in 1885, but no proof has been found. So what remains for us to have a look at, we still haven't proven that there are no zeros on the line 1 plus it, and that'll be looked at in the next section.